Yeah. Good evening, everyone. So we are ready with another interview for the Promote Science show. We have David from the University of Jena in Germany.
Actually, that's not true anymore.
Yeah.
No,
So you have now shifted to Poland.
To Portugal.
To Portugal, sorry. And so he gave a very inspiring and a very excellent talk related to the field of numerical relativity, and we will during the course of our talk we will also learn a bit of numerical relativity, what numerical relativity means and what it is all about. So thanks, David, for your precious time.
It's my pleasure to talk to you.
Yeah. So can you explain your field of research to a layman or a high school student?
I can try.
Yeah.
So the basic idea is that long ago, Newton wrote down a certain description for how gravity should work.
Yeah.
And then, for some reasons, it turned out that his description wasn't good enough for everything.
Yeah.
And in 1915, then Einstein wrote down a better version for the description, or a better description of gravity.
Yeah.
And that better description is called general relativity.
Yeah.
And so the equations of general relativity are really much more complicated than the equations that you have to solve in Newtonian gravity.
Yeah.
And so, as a consequence, that means that if we want to really understand the most extreme solutions, then we really need to use numerical methods.
Yeah.
And that's what numerical relativity is. It means the use of computation and computational methods to solve those complicated equations of general relativity. Yeah. So in a nutshell, that's what it is.
Yeah. So as we were just discussing a moment ago, so when you look like 20 years ago when you were a kid, so how do you get interested into science, or what spurred your excitement into the field of science?
In my case, it was a family member, a close family member actually, and she gave me a book for a birthday present or something. I don't remember what. But that was really the reason, because then it was a book of 1,001 questions of science or something like this. And I just gobbled that up, and then afterwards I was hooked. So it was something that I think for her was giving me the gift. It was quite an arbitrary choice of what to give me, but it had a huge influence on me and my life. So I mean, I think many people have a similar story.
So were you interested into computation or learning about very complicated equations right from your childhood or your school days?
I liked so when I was in high school, then like so many other people, I was seduced by that book of Stephen Hawking. And then at that point, yes, I was very interested in understanding all of the complicated equations. But I think early on in my scientific education, then I was more interested in these sort of philosophical questions and the beard scratching. But now I much prefer doing computations and solving real problems.
So like recently we know that the Nobel Prize for Physics went for the detection of gravitational waves, and a couple of weeks, not a couple, I mean the last week we had the announcement related to discovery of gravitational waves from merging neutron stars and the electromagnetic counterparts, which was followed up by, I mean, almost all telescopes available on the Earth till at the present moment. So that announcement actually coincided with one of the Indian festivals, Diwali, where you light so many firecrackers.
That's a nice coincidence.
So and people, and there is some tradition of buying some jewelry and some gold during that festival, just before that festival. And I guess the people out there who are watching this show right now, they must have got their answers that where all this gold from in the universe came from.
Right.
Yeah.
Now we know.
Now we know. Yeah. Now we have the solid proof that from some electromagnetic evidences. So when we talk about some kind of these some of these masses of these systems, or how these systems evolved and merged, so how does your work help us to help us to get deeper insights into some of these extreme compact stars?
Well, I suppose the main question, or the main thing that numerical relativity can do is to give you solutions to those equations with real numbers, right? So it's not just like an approximation. We can give you the real numbers, and that means that we can try and compute really, how the gravitational waves should look coming out of that system, and indeed other physics related to that, like how the formation of those heavy elements really happens. And so that's the thing that numerical relativity can offer. Although we do have to make some choices still. The modelling isn't perfect. Right. So there's the famous thing called the equation of state that we don't know. So that's something which will be a subject of huge discussion in the coming years.
So as you talked about solving very complicated equations, so what kind of computation requirements are required in order to solve some of these complex equations?
Usually what most groups working on numerical relativity would do is they would have probably a local cluster, that means a supercomputer within their group, and maybe that would have a few thousand cores, so a few thousand of the type of processors that you would have in your normal laptop or your normal desktop machine at home. And for bigger problems still, then we would usually have to apply to some national resources, and then we can work on a really big computer with even more processors inside. And so the kind of numbers that you can think of that a numerical relativity group together, one group is going to use is like 40 million core hours per year, basically. So it's as if you ran your desktop machine for 40 million hours.
I mean, that is a very huge number, right? Running a laptop for such a long time.
Well, these jobs, these computations are very expensive. And that's because we want to solve the equations, and we also want to solve them accurately. And solving them accurately means you have to use more and more computational power.
So when we talk about a high school student, or someone who is a novice related to general relativity, or specifically to numerical relativity, so what would be your advice to be such a student, who wants to get into such kind of fields, computations and solving complex equations? So where should they start?
They should study hard.
The
first thing. Well, there are different things. I mean, a key thing, of course, in numerical relativity, and also elsewhere nowadays, it has to be said in all of science, is that learning to code is a crucial thing. Right. And so the more exposure to code and the earlier, the better. I think that's fair to say. And nowadays there are lots of different good introductory tutorials and resources and so on. And so I think that it's clear. You look on the internet and you'll find something good to make a start with. I'm sure that on your outreach website you also have some suggestions for where people can start with that. In terms of the actual physics and the mathematics that people need to learn, I mean, of course there are good books for that, but in high school probably that would be too soon. And the main thing is just to concentrate on the lessons that you're learning in school, and read a lot. Read as much as you possibly can from outside outside of the syllabus,
Yeah.
like you did.
Yeah, like most of us did during our high schools. Yeah. So one more question is a bit general. So when we talk about science or maybe astrophysics in particular, so many of those. So what we observe, if we look at the history of astronomy or history of science, so what we see is like there are some theories which are given by some scientists, and there are some propositions, and then they are verified by some observations, natural observations, or some very delicate experiments, such as LIGO. So so when we talk about numerical relativity, so do we expect some kind of some hidden mysteries which where it can be the other way around, where we can observe some of those things in some merger events, and then numerical relativity can solve some of those problems?
You mean that you wonder if we can say see the waveforms, so that we see the gravitational waves coming out from some object,
some unknown object,
and then afterwards, then we can use numerical relativity to say what that object is. Well, in a way, that's already what we're doing, right? Because the waves, when they reach us, are very weak, and actually then specifying or giving values for the masses of the two black holes, or the spins of the two black holes. That's done by comparing the detected waveform against some waveforms that we know from models, and those models are all built using numerical relativity to a greater or lesser extent. So that means that we use numerical relativity to build models, and then we compare those models against the waveforms that come out that we see
in the gravitational waves.
In the gravitational waves, and then we can say by comparing the waves from black holes with two certain masses and the waves that we actually see, then we can say yes, that is that mass, or that is not that mass of say final black hole, or of the two initial black holes. So in a way that is
already being done.
That's already being done. But your question about would we actually see something very unexpected from that? I mean, it could be that when we so in numerical relativity, what we do is we choose some kind of initial setup, and then we compute to the future what happens. Right, and so it could be that something unexpected happens when we compute to the future. But that's not directly related to the detection.
The reason I'm asking is because when we look at the history of astronomy, and when we compare the different multi-wavelength fields which emanated after maybe the 1950s, so whenever a new field of astronomy popped up, there were some like unheard sources lurking out in the space-time sum out there. Like we had some theories about neutron stars. We just had theories, and after the discovery of some radio pulsars and some such objects, we came to know that these objects are really there in the universe. So there can be some
I suppose it could be that then we see gravitational waves which don't look like anything that we expected, and then somebody could come and ask us, the numerical relativity people, and say, okay, what is this thing? Can you model it for us? And at the moment, we're not doing the type of computations that we need for random stuff that we're not thinking of, because we focus on the things that we expect to see. So in that sense, you could say that there's like a sort of bias towards seeing the stuff that we expect rather than seeing the stuff that we don't expect. But I mean, of course, we could do computations of weird and wonderful things as well. But we do need a suggestion of what to actually compute in that case. So you need to tell me what you want me to evolve.
So one more question is like when we talk about like some merging compact objects, like say a pair of black holes or a pair of neutron stars. So from some electromagnetic counterparts, we can know that the final object might have been some black hole or a neutron star. So how does numerical relativity help us to understand, like, whether the final result of such a merger or neutron star merger was a black hole or was a neutron star?
Well, that's a good question, and one that numerical relativity can really answer. Right?
Yeah.
So if you give me a big enough computer, then I should be able to compute for you. If I did all of my coding and all of my equations correctly, I should be able to compute for you what happens in the time development of the initial setup. That means if I can choose the initial setup to be one that is close to the setup that was present at some stage, then I can compute that stuff to the future, and then I can find out really what happens at the end. Right? So if we have two neutron stars, of course the expectation is that if each of the two stars is sufficiently big, then after they merge, then they will form a black hole. But then you need to know what the initial masses are. And these things also depend on the equation of state that I mentioned.
What is inside those compact objects?
Right, or what they're made of.
What they're made of.
What they're made of, really. So the details matter, but what numerical relativity gives you is, if you assume those things, if you say, okay, we guess that the matter inside is described like this, then we can tell you, yes, a black hole forms, or no, it doesn't, and you're left with just some very massive star, presumably very rapidly rotating.
So one more question is related to, like, when we have the notion of black hole, I mean, if you consider a high school student or a general public, then many of them ask, like, is a black hole something where something goes in and nothing comes out? So when we consider a set of these systems which are orbiting and merging, so what happens to the surface and the event horizon? What happens to it when they merge? What happens? What is the fate of that surface?
There's this famous picture or movie even of a kind of twisted pair of pants or a pair of trousers. I suppose I'm British, so I should say trousers. And so where you see these sort of twisted legs, they go around each other and then they merge, and then you're just left with a single tube at the end, which would be the world tube of the event horizon. So the event horizon is the boundary of the black hole. It's the outermost part of the black hole. You can give a link, I'm sure, to the video that I showed. In my talk yesterday.
Sure. We will give the link of the exciting video which was shown in the colloquium yesterday. So our final question is, like, and there are many young students who are watching your interview, and there are many, the masses which are watching this video. So we know, as we were discussing a while ago, that there are many opportunities opening up in the field of astronomy in particular, and science in general, be it observational astronomy, be it gravitational wave astronomy, be it computational astronomy. This is a very important point. So what is your general message to the younger audience out there?
Come and join us. There are lots of things for you to do in numerical relativity that I don't want to have to solve all by myself. That's it.
So David, it was very nice having you on our show, and it was very nice for some of us to learn more about numerical relativity and the kind of exciting things you do, and the contributions of numerical relativists in the discovery of the gravitational waves, and helping us to understand how our universe works.
Well, thank you.
It was a pleasure talking to you.
It was my pleasure.